Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 20, Perspective Projection Matrices. In this video, the goal is to derive the formula for perspective projection. This is going to involve both matrix transformations and the perspective divide that naturally happens with homogeneous coordinates. We've talked about the perspective projections a little bit in one of the very first videos. This picture might be familiar. We have a shape called a frustum, which is a truncated pyramid style shape that defines the visible region in a scene. And so for instance, in this particular scene, you would see these two cubes, part of this blue sphere and not this yellow cylinder at all. As a more abstract diagram, I might draw it in this way. And the goal is to take this volume and map it to what is called clip space, which is the region rendered by OpenGL. It's a cube-shaped region where all the coordinates, x, y, and z, range from -1 to 1. You might remember from the previous video that the w coordinate is discarded, or rather, each of the x, y, and z coordinates are divided by that w during the conversion to this space. So we should talk a little bit about how this frustum is shaped. For example, the central axis of the frustum, kind of going from the center of the front to the center of the back, that's aligned with the negative z-axis. And you can think of the viewer as, or the virtual camera, as being at the origin. The point of the viewer would correspond to the original tip of the pyramid. So in particular, if you took these sides of the frustum, these inclined planes, and extended them, they would meet at the origin. The sides closest to the viewer and farthest from the viewer, those are both rectangular shapes. And when this is compressed into a cube shape, this back end will need to be compressed more. And that will cause objects in the rendered image of the scene to appear smaller the farther away they are from the viewer. Now, the shape of the frustum, we described it with words, but we need to define it mathematically, and we can define it by a total of 4 different parameters. First, there's the near distance, which is the distance from the origin to this first plane, and then the far distance, which is the distance from the origin all the way to the back plane of the frustum. And the near distance and the far distance, they serve as kind of absolute bounds on what you can see in the scene. There's something called the angle of view, the vertical angle of view, and that's the angle between the top plane and the bottom plane if they are extended to the origin. And finally, there's something called the aspect ratio, which is the width of this front triangle, the width of this front rectangle divided by the height of this front rectangle. And that corresponds to the dimensions of the image we want to render. And so those are the basic 4 terms explained in the 3-dimensional diagram. On this slide, also, we'll redefine them and show them from a 2-dimensional perspective. Right, so for instance, in this diagram here on the left, we get a view of the frustum from the side. That is, imagine you're looking down along the x-axis. Remember, the frustum is centrally aligned with the negative z-axis, and that's why it appears on this side in each diagram. Here we have the near distance, and here we have the far distance. And this angle right here, right, this is the angle between the top plane of the frustum and the bottom plane of the frustum. That's your vertical angle of view. And this first diagram illustrates that the angle of view, it's a kind of a measure of how much of the scene is visible to the viewer. The larger the angle of view is, the larger the frustum will become. So on this diagram on the right, the angle of view is larger than in the diagram on the left. Right? And that controls the size of the frustum. In fact, you could even use some trigonometry based on whatever this near distance is and whatever this angle of view is. You could actually even calculate the coordinates of the top and bottom of the viewing region. Now, the other perspective that we're really going to be interested in is the aspect ratio. In this diagram on the right, we see the front of the frustum as if we were looking down along the z-axis. The aspect ratio is the width of this region divided by the height of this region, and these dimensions are chosen to match the aspect ratio of the image that you're going to render. Right? And once you know the top and bottom values for the y range, you could combine that information with the aspect ratio to figure out the range of x values. You could also use a horizontal angle of view, but it's a lot easier to work with the aspect ratio so your image appears without distortion with the dimensions that you'd like. All right, to actually calculate where points in the three-dimensional scene will end up, we're actually going to do some projection. So the idea is to take points within your frustum. Here we have 3 points, a red point, a green point, and a blue point. We want to see where they would end up. So this front rectangular region of the frustum, we can think of that as our projection window. To see which points on the projection window correspond to the different points within the frustum, connect the points inside the frustum to the origin with straight lines, and wherever each of these lines intersects this front rectangle, this projection window, those intersections are where these points will show up in your rendered image. So that's the idea on how projection works. Still, we have to do the mathematical calculation now. If you know the coordinates of these points, how will you find the coordinates of these 3 points here? And also at the same time, remember the ultimate goal is to convert everything to clip space. We want to take this frustum shape and compress it into a cube-like shape. So we'll break this up into a few steps. The first step is going to be to adjust the projection window. So effectively, we'll start by working with the y coordinates. We know that the y values, they need to be between the range -1 and 1. And so we'll assume that we have a new adjusted projection window that perfectly fits those boundaries on the y-axis. And let's also assume that we want to keep the same angle of view. However, this means that the distance between the origin and the projection window, that distance is going to change. Now, you're changing the height of this window so it fits within these bounds. If you keep the angle the same, something's got to change. In this case, it's this distance here. What we'd like to do is calculate the distance to this new projection window, and we can do that with a little bit of trigonometry. In fact, if you take a look here, we actually have a right triangle. Since we're only looking at the top half of this part, this angle is a over 2, where a is the angle of view. We know that the height of this right triangle is 1, and we want to calculate the distance. And in this case, we'd use the tangent function, since the tangent of an angle is equal to the opposite side divided by the adjacent side. So we actually know that tangent of a over 2 is equal to 1 over d. And then using a little bit of algebra, we can rearrange that equation. And the result is, we know what this distance is. The adjusted projection window is this distance, 1 divided by tangent of a over 2, units away. Also, should mention that this is on the negative z-axis, so points along this line we'll have z coordinate equal to negative d, negative this distance. And because the distances, the lengths of a side, should always be positive numbers, but we have to correct the sign depending on if we're on the negative side of the z-axis. All right, so keeping this triangle in mind, we're going to come up with a formula for projecting the y-coordinate onto this new window, and that's our next step. In other words, let's say we have some point within our frustum, we'll call that point P. We want to project that onto our new projection window, which is illustrated by this gray line. As we mentioned before, the way we calculate a projection is we draw a line from this point to the origin and see where that line intersects the projection window. And that's the projection of the point onto the viewing screen. So what we notice here is if we draw this line, and if we also drop a perpendicular line from P down to the z-axis, what we actually have here is two similar triangles. Right, both these triangles are, I've got a small triangle here, then I have a larger triangle with these three edges. Right, both of them are right triangles, and both share this angle here. This isn't a over 2. A over 2 would be the full frustum, but this is a smaller angle. So they share that angle, so these third angles must be the same. We know that the triangles are similar. And the reason this is important is that in similar triangles, the sides are proportional to each other. So that means that the ratios of the different sides are equal. In other words, for this large triangle, this edge, the vertical edge, divided by the length of the base is equal to the vertical edge divided by the length of the base for this smaller triangle. And that gives us this equation right here. And notice these negative signs. Right? We know that according to this diagram, the y values are positive. And I really want to use the lengths of these sides. But because everything's happening on the negative z-axis, I need to use the negatives of the z-coordinates to get positive numbers to give me the lengths of the base. And so I get this equation from the similar triangles. And I also know the value of QZ. Right? Any point on this adjusted projection window has z value equal to negative d. So we could substitute that in here and then rearrange a little bit to solve for QY, the y value of the projected point. Right? And so that value is given by this expression right here. And one of the things you might notice is that this isn't really a linear transformation. Right? Linear transformations involve multiplication and addition, but not division like this. But fortunately, we're working with homogeneous coordinates. There's a built-in perspective division step, and so that's going to allow us to write this transformation. And so as we just mentioned, the formula that involves dividing by a z component, that's not a linear transformation, so we can't rely on just the matrix. Now, as a refresher from the last video, perspective division is how we convert homogeneous coordinates, x, y, z, w, into regular three-dimensional coordinates. We divide each one of the first three components by the w component. Right, so to get this formula, what we'll do is we're going to multiply our point by this matrix. Here the asterisks, they represent values that we don't know yet. But I'm going to say that second row is 0d, 0, 0 in the matrix. And kind of the trick we're going to use, since we want to divide by the z value, we're going to change the last row of this matrix. Right? When doing ordinary geometric transformations like translation or rotation or scaling, this last row is 0, 0, 0, 1. But for the perspective transformation, we want to divide by the z component. Technically, we want to divide by the negative of the z component. So we'll use this last row to effectively move the z component into the W position. And so if we use this matrix here and multiply it by the point in our frustum, we're going to get this point. And we don't know what the first and third coordinates are because we don't know what the first and third rows are. Then we get this point, and we do know that once perspective division happens, which is automatically handled by the GPU, this 4-component point will turn into this point. Right? Each one of these first 3 values is divided by negative PZ. And that gives us the formula from the previous slide. Right? The transformation we want to do, the value for QY is given by this formula. And sure enough, that can be accomplished with a combination of a matrix multiplication and the perspective division. All right, so that takes care of the Y coordinate. As you may have guessed, calculating the X coordinate is very similar. Right? In this case, I'm drawing the diagram slightly differently. Imagine now we're looking down along the y-axis. The positive z-axis is pointing forwards, a positive x-axis pointing to the right. So the frustum, again, is on the negative z-axis. Let's discard the y components to make the diagram easier to read. Let's say we want to project this point P onto the projection window. So once again, we draw that line connecting P to the origin. We want to see where it intersects. Once again, we have similar triangles. Once again, that tells us that sides are proportional to each other. Ratios of sides are equal. And that leads us to this equation. Looks just like the equation when we are working with projecting the y coordinate, except those y's have become x's. And again, QZ, any point on the projection window, has z component equal to negative d. So we plug that in here, we do some rearranging, and we get a formula for qx, the projection of the x coordinate. Now we're almost done, but there's one more thing we need to take into consideration, the aspect ratio. Right? We started adjusting the projection window so that the y values were automatically in the range from -1 to 1. Now the aspect ratio tells us the dimensions of the image we want to render. If the y values go from -1 to 1, then the x values in the image we want to render, those are going to be ranging from -r to r. But we're trying to transform this into clip space. Everything we want to show up needs to be within that cube. In OpenGL, where all the coordinates are between -1 and 1. So we need to take this range, we need to scale it down, we need to divide by r. And that turns the range from -r to r into the range from -1 to 1. Right? And so this tells us what we need to do with the next part of the projection matrix. We can actually fill in the first row now. Right? The first row looks a lot like the second row, because it's translating the x coordinate in a very similar way, except we have that extra division by r. And so again, this will become multiplied and give us this result in the first component. And after we do the perspective divide, this first entry will be divided by negative z coordinate. We're almost done. The last step is to fill out this last row of the matrix. Now, what do we know? We know that the z values between the near and far distances, those should be mapped to the range from -1 to 1. We also know that the x and y components really have no effect on how far away the z component is from the camera. Right, so when we're writing out this third row, we'll write it in the most general terms possible for now. Since x and y should have no effect on this component, we'll put zeros in these first two spaces. So the x and y will be multiplied by zeros and have no effect. The other entries, we're not sure what they should be yet, so we'll just fill them in with some constants, b and c, and we'll solve for those later on. Now, what we know is that once we do this matrix multiplication, we get this result. And then after perspective division, this third component, b times pz plus c, that gets divided by negative pz, and we have this result down here. Negative b minus c divided by pz. Now, to solve for these two constants, b and c, we need to use the information provided by the near and far distances. Right, so we'll get a system of equations, but there's 2 points we need to be really clear about, otherwise we'll accidentally introduce more negative signs and confuzzle our equation. The first thing we need to keep in mind is that near and far distances, they're usually given as positive numbers. Right? A distance from the origin, you would think of that as a positive number, but the frustum is aligned with the negative z-axis. Right, so the lower limit, the closest points to the camera, will satisfy their z component being equal to negative n. The furthest points from the camera, they'll have their z component equal to negative f. Okay, so that's one thing we need to keep in mind. The second thing is we need to know if pz is equal to negative n, then this value right here, it should either be mapped to -1 or +1, and you might think, I know that I thought, that initially this should be mapped to +1, because in the coordinate system we've been using, the positive z-axis points at you, the viewer. So the near distance should be +1. But the default setting in OpenGL, when it does the depth test comparison, it's set to a constant called GL-less. And basically what's happening is when performing the depth test, a point is considered closer to the viewer if its depth value is smaller. This is backwards than the coordinate system we've been used to, right? So it turns out near values in our coordinate system should correspond to -1, right, which is a less or a smaller value when OpenGL does its depth test. Right, so our first equation is going to be when pz equals -n, then this coordinate should map to -1. And analogously, far distances in OpenGL, the depth test says that they should correspond to greater values. So this expression should be equal to +1. So these two facts will give us a system of equations. If we substitute -n for z here, that'll give us our first equation. The negative signs cancel, giving us a positive. And in the second if-then statement, substituting a -f in here gives us a second equation. And whoops, that should actually be a positive sign. Sorry about that. This is a positive sign. So when you solve the correct equations, where this highlighted should be a positive sign, the solution, well, it takes a little bit of solving. You can multiply the first equation by -1, add it to the second to cancel the b's. Then you could solve for c, and you'll find out that it's this. Similarly, once you find the value for c, you can plug it into this first equation and solve for b. You'll find out that this is the value of b. And that tells you everything you need to know about the projection matrix. So, to sum it all up, this is what the projection matrix looks like. If you have a frustum, which is defined by these 4 parameters, a near distance n, a far distance f, a vertical angle of view A, and an aspect ratio R. And you're working with homogeneous coordinates, so this is a 4x4 matrix. Right? But this matrix, combined with the perspective division, which happens automatically, is going to allow you to create a perspective viewing effect. And in our previous version, we had written d divided by r and d in these 2 locations, but I just substituted the values of d in terms of a. So this will be an extremely useful matrix to give our scenes that three-dimensional perspective.